So this is Michael Hind. You of course all know him, and he's going to talk about myths of dynamic optimization.
Thanks, and I have to keep this down to 30 minutes because I set the wrong tape speed, so the tape is going to run out. Real incentive to get to lunch on time. So the point of this talk was going to be debunking dynamic optimization myths, things that people may believe are true, but I think given people who are in the crowd, I probably should have went with something like telling you something you already know, maybe. This was a PLDI tutorial we gave a few months ago, Steve, Fink, and Dave Grove and I. So I've stolen 3 hours worth of slides and compressed it into 28 minutes, really. Okay, so here are some well-known facts. Because dynamic compilers are executed at runtime, they must be blazingly fast. It's the only option. Dynamic class loading is a fundamental roadblock to doing things like interprocedural analysis. Everyone knows this. Sophisticating profiling, forget it. You can't do it at runtime. It's too expensive. A static compiler obviously will always produce better code than a dynamic compiler. Program optimization, forget it. It's a dead field. And if you're at a university and you don't have a lot of resources, it's impossible to do any kind of research in virtual execution environments. It's just too complex. There's just so much infrastructure you need. So those are the so-called facts. So hopefully someone believes at least one of these.
Raise your hand if you believe it.
Yeah, at PLD I actually asked that question. Does anyone believe any of these things? And it was grad students and they didn't want to raise their hand. What was coming. Okay, so I'm just restating again. Basically, the idea here is, it's a dynamic compiler. You don't have time to do things sophisticated like graph culling register allocator and so on. And just take a step back here. How a program is executed, I think we all know this. There's at least two options. You can interpret, or you can do what we're calling classic just-in-time compilation, meaning the first time the method is invoked, you call your JIT compiler and you compile it. Right? And this mechanism, I think, is responsible for some of the myths, because if you believe that whenever you execute a method you have to compile it, then that's going to be a lot of overhead. Right? But in reality today, people use a technique that we're calling selective optimization, which is basically a simple idea. You initially assume code is not important. You interpret or use a non-optimizing compiler, and you magically find out where you're spending your time, and then you use your full-fledged optimizing compiler for that hot subset. And most of the commercial VMs use this, in fact. Here's some examples. There's work actually in the early 70s on adaptive Fortran at a CMU that used an interpreter and two compilers. Of course, the Self system used this, and almost all the JVMs use this. And you can see there's different techniques. Some folks use an interpreter and one or more compilers. Some use multiple compilers. Okay, so just some data to show you that this actually works. I happen to have a JIKES REM data, so that's easily available, so I just use that. What you see here is a whole bunch of benchmarks. Ignore all that, just look at the average for now. And what this is 4 different configurations. Basically, there are 4 classic JIT compilers. One is a non-optimizing compiler, and that's the baseline. That's 1. Okay, that's the performance you get there. And then this is basically saying if I use a JIT compiler with basically op level 0, 1, and 2, think static GCC or whatever optimization levels, what do I get in terms of performance? These benchmarks all we're calling short-run benchmarks. It's in these spec benchmarks. It's one iteration. They run for anywhere from a few seconds to maybe about 30 seconds. And what you see is not surprising. The more optimization you do, the more cost you get. The worse performance you get, the more overhead. So it gets worse. And in this case, you do either light optimization or no optimization at all. It works out well. If you use a selective optimization strategy, surprise, surprise, you actually can do pretty well. And the select optimization strategy, in this particular case, is choosing one of these 3 levels to apply to the hot parts of the application, and all automatically online. And this is not specific to JIKES RVM, other systems do this. Yeah.
So obviously you selectively optimize. So you're only going to run it, on a small piece of code. It'll go fast. But you still have to have the memory. It seems like you have to have the memory footprint of this highly optimizing compiler and all the data structures it generates.
Yes.
Is that accurate?
That's accurate. That's very accurate. Yes.
And you still have to do the cross-module analysis of modules that you're not even optimizing, right?
I'll get to that. We'll get to that. That's not a myth. And here was similar benchmarks, but now run for a longer time, so-called steady state. And here we also get benefit of improvement. This is probably a little too complicated to explain. Let me take it offline if there's questions about it. So the point here was that it works for short running and long running. Another completely independent system, this was the IBM DK, also known as the IBM VM. Slightly different configurations. The message here is these are the ones that use a selective optimization strategy. They use a mixed mode interpreter and then something like a quick optimization or full optimization. And these guys do pretty well compared to here. And then if you look at longer running programs, they do pretty well compared to the corresponding bar. So it's not a perfect way to show this, but I think you get the idea. And I'm sure we can look at Hotspot and other VMs and get similar stories. So hopefully I've convinced you that if you believe this myth, it's not really true. Production JVMs now, commercial JVMs, have a lot of classic optimization. There is graph culling register allocation. There is SSA form, and so on and so forth. Okay. The second bullet talks about type information, and we have that for discussion later, so I won't go into that. Okay. Myth number 2: dynamic class loading is a fundamental roadblock to cross-method optimization. If you don't have the whole program, how can you do anything like interprocedural analysis? Right? That's kind of what Andrew was touching on as well. And the answer here, Bob touched on earlier, is basically speculation. So you can generate code that is correct for the current program you've seen. So the program is loading as you run, and you've got code. You can speculate based on what you know so far that this will be the final number of classes that get loaded. This is the world as you know. And then if you're wrong, something gets loaded, you can go fix that. That's the idea. And then how do you fix that? Well, that's the catch, of course. There's a general technique called on-stack replacement and another technique called pre-existence inlining. I'll just spend a little bit of time on that. On-stack replacement is pretty much what it suggests. You have a method that's on top of the stack, it's running, and now you've got to rewrite the activation record because you just changed it. It was speculating and it was incorrect. So you got incorrect code there. You've got to rip it off the stack and put the correct code on there. And so there's mechanisms for doing this. Hotspot does this. Jike's RVM now does this. If you have this mechanism, then you can do a lot of cool things. You can basically say, I'm not going to compile this part of the method because I don't think it's going to ever get executed. And then if it does, then you go and you do, you fix it up. If you happen to get stuck in a loop, if you don't have on-stack replacement, quite often what you have to do is you realize this is an important loop. You generate new code, and you've got a much better version of this method with the loop in it, but you can't jump to it because you're stuck in there. So if that happens to happen, and it happens in one spec benchmark, then it's nice to have this mechanism to get you good spec scores. Maybe it happens in the wild. Now there was work in the early 90s about debugging optimized code. This can be useful to recover state for that. There's some patches, of course, and Cliff can, I think, talk for several hours about this.
But it works.
And it works, yeah, it's cool stuff. Okay, and then speculation in general. There are some challenges. The biggest, so as engineer, you can read this. This one I think is really interesting, and that is on-stack replacement happens when you think something was going to happen, right? Which is you speculated on something, and then it turns out that you were wrong, right? And then you're going to now jump into some code that's going to try to fix things. That's probably not going to happen too much, so testing that is going to be a real challenge and a good place for bugs to hide. Pre-existence is a nice observation that was made in the late 90s that basically says there's some special cases where you can actually speculate and you know that it's actually not going to be incorrect. I'm going to skip this because I'll probably get it wrong when I explain it. But I can talk to you offline. It'll be less pressure. So in summary, myth number 2 is I'm going to disagree with what Andrew was saying in that, yes, you can't do static whole program analysis and prove things will never happen, but you can speculate, and if you've got a mechanism to recover, you can get the benefits.
That wasn't exactly my question.
Okay.
The question was not, you can't do whole program analysis because you haven't yet loaded the whole program. It was that the analysis you have to do is proportional to a big part of the program, but you're only optimizing one method.
Right, so your scope of optimization is smaller. So inlining will try to help you with
But isn't this also an answer to that? Maybe we should take that offline
Yeah,
since
I
my
mean,
Yeah.
opinion is short of time. But you could analyze a small part, and if you find out later you executed another part and it was wrong, you treat it as if it was just loaded. I don't know.
You know, we do this all the time in Hotspot. There are regions of code, you know, people write exception handlers that are never taken. We just write the bailout to the interpreter on that path, and we cut off optimization there.